Hello friends, this video on solid states part 22 is brought to you by examfear.com. No more fear from exam. Now let's talk about some electrical properties of the solid state. In fact, solids, they exhibit amazing range of electrical conductivities ranging from 10 to the power minus 20 ohms per meter to 10 to the power 7 per ohm per meter. That is the range of electrical conductivity, 10 to the power minus 22 to 10 to the power 7. Correct? In fact, there are three types of solids based on conductivity. They are conductors, they are insulators like wood, and there are semiconductors like transistor, silicon. Right? So conductors typically have the conductivity range pretty high, 10 to the power 4 to 10 to the power 7 per ohm per meter. If we talk about semiconductor, then it is little less, that is 10 to the power minus 6 to 10 to the power 4 per ohm per meter. So you see, this range is matching. If we talk about insulators, have all the more less, 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. That is the range. So solid has a huge range of electrical conductivity, right? So if you see, these wires are used because these wires are conductor and they are used to glow bulbs or any electrical wirings. Have you ever thought why metal is a conductor, wood is not a conductor, and silicon is a semiconductor? Who is playing the role here? Right? It is electrons. It is electrons which is playing the role here. We'll see this now. Right? Let's see the electrical conduction in metal typically. So typically what happens is, so this is the electron, it flows here and it goes to the positive side, and see the circuit is complete. So this is my metal, the one which you see. It's copper metal actually. There is a negative charge attached here, the battery. The electrons moves, right? And then the circuit is complete, and we say that copper is electrically conductor, right? See, this is how it works. Now the question is, why it works fine in case of copper but not in case of wood? There has to be some reason, right? Why it conducts, copper conducts but not wood? To understand the conductivity of these, let's go into the quantum world, right? So if you see a typical atom structure, this is how it is. So we have atom, we have discussed this actually in the earlier slide. We have atoms and we have this electrons, right, jumping around in different shells. So we have 1s orbital, 2s orbital, 3s, 2n, and each of these orbitals have different energies, right? So we create an energy band because 1 has lesser energy, 2 has more energy. So we can create an energy band like that, right? Because let's suppose this one has x energy, 2 has x plus y, 2p has x plus y plus z. It keeps on increasing. So we can have different energy band, correct? And we see that the moment you give some energy to the electrons jump from one energy band to another, correct? So if you see, you give some energy to this electrons, you have seen this actually, this electron jumps, and when it comes back it emits light, but if you give some energy to it, the electron will jump from one orbital to another orbital, correct? Now if you see the concept of energy band, as I told, since this electrons in the atoms, they have different in different orbitals, and the orbitals have different energy bands. So for example, hydrogen has only one band, helium will have one band, lithium will have two bands, right? This is a 1s band, this is 2s band, 1s band, 2s band, like that, right? If you talk about silicon, we have 1s band, then we have two band, band 2, this is band 3. This 2 band will have 2s and 2p, and this 3 band, third band will have 3s and 3, like that. There are different energy bands, right? They are nothing but the large number of closely packed spaced energy levels, right? They are nothing but energy levels. Correct. Now understand this. Now we know what is energy band. So we have something called valence band and conduction band. There are two different types of energy band itself, right? So if you see, what is valence band? So valence band is nothing but, if I have the sodium, right, the last my valence electron is in this band. Correct. So that is my valence band. See, valence band is nothing but the band in which you have valence electron. For example, in sodium, I have electron configuration 1s2, 2s2, 2p, 6, 3s1. So 3s1 is the largest band I have. So this is my valence band in this case, 3s1, the maximum one, because this is the one where I have valence electron. Now, if my electron somehow jumps out of this band and goes to some other band, because there are so many bands, right? If my electron jumps and goes to some other band, let's suppose it goes to 3p band, there will be some 3p band here also. Correct? There will be more band. Because see, these bands which I am drawing, actually if you see atom, you don't see this band, right? They are all virtual. As I showed you, just the figure, the electrons actually don't rotate or revolve in this path. They jump, they just keep moving around here and there, right? In specific orbitals, and these orbitals have the bands. So if this electron jumps out of this band to a higher band, electron is free. And if electron is free, it is free to conduct, because for conduction of electricity we need free electrons. Correct? So the conduction band is higher bands. So if the conduction band and the valence band are close, small energy can easily excite this valence electron to jump out and take part in conduction of electricity. It will become conductor. If this energy difference is very high, we'll show that, then in that case it will not conduct. We'll talk about that. Just understand this is something called valence band, conduction band, right? So valence band is the one, we have the valence electron, so the energy corresponds to that, this valence band. And conduction band is the band where if the electrons are present, they are free, right? That band is called conduction band. So we have talked about this in the Bohr and the quantum theory. So this is the typical understanding of valence band and conduction band. Same thing with silicon also. We see there will be some conduction band here, right? Chlorine also will have conduction bands and valence band. So now let's see the valence and conduction band in conductors. So in conductors, if you see, the valence band and conduction bands almost overlaps. It's very easy for electrons to go from valence band to conduction band. So if you take this example of a conductor, for example, sodium typically don't exist as sodium atom, one sodium atom. There are tons of sodium atoms that are together. So in this case, there are so many atoms together. There's a repulsion also between the sodium atoms. So with that repulsion, the outermost electron are easy to kicked out, right? Because the repulsive force, they can easily be kicked out. They are almost out only, always. And thus, they are in the valence band. Correct. So the valence band and the conduction band is almost overlapping. So conductors, they generally conduct electricity because of flow of electrons or ions. So electrons is generally metals and ions is generally electrolyte. For example, NaCl, we mix in water and it conducts electricity. That's a different story altogether. For metals, we generally talk about electrons, right? So metal conduct electricity using electrons, and they conduct electricity both in solid and liquid state, molten state. But these ions conduct electricity only in the liquid or molten state, not in solid state. So we'll generally focus on the solid metals now, right? So this conductivity of the metal depends on the number of valence electron available per atom. So if it has one atom, two atom, that determines the conductivity of this metal. So I've just discussed the atomic orbitals of these sodium. They form molecular orbital, right? And we have discussed this molecular orbital concept. And these are molecular orbitals are close in energy to each other, and they form various bands. And if this bond is partially filled, right, or it overlaps with the higher energy bands, which is unoccupied, because there are so many other bands, right? So the higher band which are unoccupied are conduction band. And if the difference is less, the energy difference is less between the valence band and the conduction band, in this case, for example, of conductors, the electrons can easily jump to conduction band, even by application of small electric field, and thus they are conductors, because the valence band and conduction band is almost overlapping. In case of insulator, if you see, there is a huge difference in the valence band and conduction band, right? So even if you give some energy, electric field, this electrons will not be able to jump from here to here. Since the electrons will not be able to jump to conduction band is a free pool kind of stuff. So it won't be able to conduct electricity. For example, wood, right? Chlorine is also one example where the gap is pretty high, right? So it is not able to jump. Same thing, you see a lot of chlorine molecules, but even if you apply electric field, these valence electrons from the chlorine will not be able to jump. The next is semiconductors. So in case of semiconductors, for example, transistors, we use semiconductors. So the gap between the conduction band and the valence band is there, but it's not that much. It is small, right? So in that case, some electron may jump. So if there are, let's suppose, 5 electrons, out of that only 1 may jump. Out of 4 only 1 may jump. Some may jump. So it shows some conductivity, but not full conductivity. And this is a very good property actually. You know, with that, the whole computer world is made of silicons, the semiconductors. Because with that, we are able to form different kind of diodes, transistors. We'll study about this. So electrical conductivity of semiconductor increase with increase in temperature. So conductivity, I'll say here, conductivity is directly proportional to temperature, right? An example is silicon, germanium are good example of this. And they are also called intrinsic semiconductors. Why? Because this pure silicon and germanium has very low conductivity. They are also called intrinsic. That is pure. They have very low conductivity, but you can increase the conductivity by adding suitable amount of appropriate impurity. So here impurity is helping. That is called doping, right? So you add, please notice, some suitable amount of appropriate impurity. You add this, and this process is called doping. We'll talk about this, right? For example, silicon is a semiconductor, correct? So, thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.